So although this is a talk about a theorem in birational geometry, the applications are all in arithmetic. So my talk is going to be sort of the arithmetic motivation and why this theorem implies arithmetic consequences. So Faulting's theorem says that on a smooth curve of genus G greater than or equal to 2, defined over a number field K, the set of K rational points is finite. Okay. Right. But of course, this doesn't tell us anything. It's sort of like effective bounds range. It just says if I have a smooth curve of genus G greater than or equal to 2, which means a curve of general type, the number of rational points are finite. Okay. So sort of a natural question that one could ask is what happens to this number of points as the curve varies in a family? Right, so if I have a family of curves, so if I have a curve of general type, it has finitely many rational points. But for instance, the total space of a family of curves of general type could easily be rational. Okay, and so the rational points could be potentially dense in the total space. Okay. So what we want to do is come up with some sort of uniform bound for the number of rational points that does not depend on the curve, but depends only on things, say, such as the genus and the number field. Right, certainly the number of rational points will depend on the degree of the polynomial. So this is where the genus is coming in. And it's certainly going to depend on the number field. Okay. So this was made precise in the uniformity conjecture of Caparaso, Harris, and Mazur. Okay. So let K be a number field. Then there exists an integer. Okay, so I'm going to call it B, K of G. So it depends on the number field in the genus, so that any smooth curve of genus greater than or equal to 2 has at most B, K, G, K points. Right, so this conjecture would give a uniform bound to the number of rational points on a curve of general type that depends only on the genus of the curve and the degree of the number field. Okay. And so the theorem that Caparaso, Harris, and Mazur prove is that this conjecture is true if you assume Lang's conjecture. So Lang's conjecture implies uniformity. Okay. All right, so let me state Lang's conjecture. Roughly speaking, Lang's conjecture says that if I have a variety of general type, then rational points are not Zariski dense. Okay, and what this theorem says is not only, well, is there some finiteness property, there's actually some uniform boundedness. Okay, so Lang's conjecture if X is a variety of general type, defined over K, then the set xk is not Zariski dense. Okay, so this is in contrast to the case of, say, X rational, where we know that the rational points may be dense. Okay. Okay. All right, so let me, before getting into, let me say what a variety of general type is. So X is of general type. So there's two definitions that I'm going to use that are equivalent. So one is that X has canonical singularities. Okay, so what this precisely means is not so important. It's just a condition that says that X has mild singularities. And we know, and we require that the canonical sheaf is big. Okay. Equivalently, we could say that if I take any variety, so X is of general type, if for any desingularization, this smooth one here is of general type, so omega x tilde is big. Okay? And so canonical singularities precisely means that the sections of the canonical lift to the sections of the new canonical under the resolution. Okay, so these definitions are equivalent. Okay, so some examples and non-examples. Okay. Okay, so Pn is not of general type. Right. So things that are rational are not of general type, right? Omega x has no sections. But a smooth curve of genus greater than or equal to 2. So in particularly a smooth quartic curve. This will be important later. Okay, but if I have a quartic curve with 3 nodes, then it's not of general type. A quartic curve with 3 nodes is rational. Okay, so the singularities are very important. Okay. Okay, so how does Caparazo, Harrison, Mazur prove this theorem? I told you it's a purely algebraic geometry theorem. So their theorem that says uniformity follows from Lang's conjecture is a consequence of the following theorem, which is the main theorem of their paper, which says let f from x to b be a proper morphism of integral varieties. So that the general fiber is a smooth curve of genus G greater than or equal to 2. Then there exists some n sufficiently large and integer. And a morphism from the nth fiber product of x with itself, so I'll say what that means in a moment. Okay, so I should say it's a dominant rational morphism to W, a variety of general type. Okay. Good. Okay. So if I have a family of curves where the general fiber is a smooth curve of general type, then maybe the total space is not rational. And maybe some power of the total space is not rational, but it will at least give a dominant rational map to something which is general type. Okay. And so then the idea is that we're going to assume Lang's conjecture and show that this implies, so I wrote morphism and it should be map, dominant rational map. So we're going to use Lang's conjecture and show how this theorem implies uniformity. Okay, so there exists a positive integer sufficiently large and a dominant rational map, x and b. So let me define what x and b is. Okay. Okay, so x and b, let me get a piece of chalk here. So x and b, I just take the fiber product of x over b n times. And because I assume that the fibers are integral, there's a unique irreducible component inside here. Okay? Okay. So why does this theorem imply uniformity? of course, assuming Lang's conjecture. Okay. Good. And so what I'm going to do is I'm going to take sort of the simplest non-trivial example and show why it's true, and then explain how you generalize from that example to a more general case. So, are there any questions so far? So let X be the hypersurface in P1 cross P2. Okay. Coming from the family of quartics okay, so I take two quartic curves and I take a family. Right, so in the general fiber is a quartic curve, which is the general type. Okay. Okay. So then X is not of general type. Right, so X is the total space, and it's not of general type. Okay, and you could see this in two ways. One, you could see that it's rational because it's the blow-up of the 16 base points of this family. Okay, so one is the blow-up of 16 points, P2. Alternatively, we can compute the canonical bundle using a junction. And this is going to be important for later, so let's do it anyway. So omega x, so omega P1 has crossed P2. Then, did I do P1 cross P2? Yeah, 1, 4 times O of x. Okay. And so what do we get? We get minus 2 and 1, so we get O of minus 1, 1. Okay. And this is certainly not big. Okay. We have this minus 1 here. So this is not big. Okay, so X is not of general type. But what we're going to see is that once I take the second fibered power will be of general type. So I'm going to call this Y. So this is X cross X over B is of general type. Right, so what, just for the sake of saying it, what is the second fibered power look like? Well, I take fxy plus t gxy. Right, it's locally two copies of. Okay. So it's the hypersurface given by this. So it's actually, so y is a hypersurface inside P1 cross P2 cross P2. And it's the complete intersection of something of the form 1, 4, 0 and 1, 0, 4. Okay. So I have something of the form 1, 4, 0 and something of the form 0, 4. Okay. Yeah, sorry. Okay, so we can compute the canonical. Okay. So we want to show it's of general type, so we compute the canonical and we show the singularities are okay. Okay, so we do the same sort of thing. Okay, so now I have something 1, 4, 0 and 1, 0, 4. Okay. Okay. So now what do I get? I have minus 2, 1, 1, so I get O 0, and then I get 1, 1. Okay, so this is big. But remember, we had two things that we had to check. If it's general type, we have to also check the singularities are okay. And the singularities are okay because we start with a family of curves, so the fibers are at worst nodal. Okay? And so remember, this thing locally looks like two copies of this. So locally of the form xy equals uv inside a smooth fourfold. Okay, and I'm not going to do the calculation, but I promise these are canonical singularities. Okay. Okay. So what we have is that this family itself, the total space is not of general type, but if I take a fibered power, it is of general type. Okay, and remember in general, I said that you map to something of general type. So this is sort of an easier example, but I'm going to show first why it works in this case, and then how to generalize. Okay. So assuming Lang's conjecture, there exists a closed subset called Z2 inside of Y, containing all the rational points. Right? Because Lang's conjecture tells me that the points are not Zariski dense. So I have this closed subset. Now I have two maps. I have a map pi2, which takes y to x. It's just a projection onto one factor. And then I have a map pi1 that takes x to b. Okay? And the fibers of these maps are the same. Okay? And I can restrict. And I should also note that they're both, well, not yet. So I'm going to restrict, let me first restrict pi2 to z2. Okay? And I could look at the image of z2 under this map, and I'm going to call this z inside x. Okay? And now pi2 here is a generically finite map, right? Because the fibers have finitely matched over an open subset, the fibers have finitely many rational points by Falting's theorem. And the same is true for if I look at pi1. Okay, and I'm going to call the degrees of these maps d2 and d1 respectively. Okay. So now there's some open subset. You're not inside the base where the fibers are finite, right? This is because of Falting's theorem. Okay. So take some point inside here and look at the fiber. Okay. And ask if all of the rational points are inside this fiber. So if all rational points are in XB, then there are D1, right? Because that's the degree of the map. Otherwise, we just lift up to the top. Otherwise, look at fiber of pi2. And by construction, this set Z2 must contain all of the rational points. So if they're not here, they must be here, upstairs. So in conclusion, you just take the max of D1 and D2. Okay. So now how does this give the uniform bound in general? So there's a few things that need to be done. So one, you use Noetherian. Okay, so how to generalize this? So one, you have to do Noetherian induction to get rid of the fact that I did this on some open subset. Right? And the point is the complement keeps getting smaller and smaller. Two, so in general, I have x and b has some rational map to some variety of general type. I have Lang's conjecture here. I have a closed subset. I look at the pre-image and I repeat. Finally, I use the existence of a Hilbert scheme to tell me that I can find any genus G I fix a genus, I can find any smooth curve of that genus in some family. Okay. Okay. So this is essentially how uniform boundedness follows from the fiber-powered theorem once you assume Lang's conjecture. Okay. Okay, so this is the case of families of curves. For results. Okay. So Hassett proved the same thing, essentially. He proved the fiber-powered theorem for surfaces of general type and then obtained similar uniformity results, so surfaces of general type. Okay, so things get slightly trickier in higher dimensions because you might have a variety of general type. Well, you definitely have varieties of general type that contain subvarieties that are, say, rational. Okay, so you have to, the results are slightly different, but in the same general idea. And then, so Abramovich, Volach / Abramovich, in 2 papers proved this theorem for varieties, all positive dimensional varieties of general type. So Abramovich-Volach proved that uniformity is true, assuming there exists a fiber-power theorem, and then Abramovich actually proves the fiber-power theorem. So I should say, just for the sake of context, the proof of the fiber-power theorem relies heavily, so in this case relies heavily on the existence of the moduli space of curves. This theorem here relies on the KSBA compactification of the moduli space of surfaces. And in this case, sort of semi-stable reduction was not yet known, so Abramovich had to sort of work a little bit by hand and use de Young's plurinodal reduction and do things much more explicitly. Okay, so are there any questions so far? Okay, so the goal of my sort of research program, which is joint with Amos Turkett, who's a postdoc in Sweden, is to extend these results to pairs of log general type. Using the Voigt-Lang conjecture. Okay, so the Voigt-Lang conjecture is the generalization of Lang's conjecture to pairs of log general type. Okay, so what's a pair of log general type? F. Okay. Okay, so by a pair I mean I have a variety and a divisor. Okay, so X is a normal variety and D is some divisor inside X, and I want the pair to have log canonical singularities. Unfortunately, I have no time to explain what that means, and I want omega X twisted by D to be big. Okay. Okay, and so sort of the idea is that, for instance, if I take P2, it's not of general type, but if I take P2 and I take some smooth curve, say a quartic curve P2, and a quartic curve is of log general type, because it certainly has nice singularities. And if I take omega of P2, which is I get -3, and then when I twist by the quartic curve, I get O of 1. Okay, so that's big. So if I take P2 and a smooth quartic. Okay. And so somehow the idea is that we want to talk about integral points on some variety away from a divisor. Okay. So let me say. So the first thing we do is we prove the analogous fibered power theorem. So I have a family of stable pairs. So this is the generalization of, say, stable curves in higher dimensions and to pairs, family of stable pairs. Where the general fibers of log general type, so in this case has log canonical singularities. So the fact that these are stable pairs already guarantees that omega X is big. Omega X twisted by D is big over a smooth projective base B. Then after a birational modification of the base, okay, then the same thing is true. There exists an n sufficiently large so in this case we actually get a morphism. So xn b tilde d tilde n admits a morphism to W delta, a pair of log general type. Okay, so unfortunately a 30-minute talk, I have no time to explain details, but you might ask if this birational modification of the base is important, if it sort of ruins the arithmetic applications, but it doesn't, because the definition of log general type used by number theorists is slightly different. Okay, and we proved two theorems. We proved this theorem in this case. We also prove a theorem in the setting of what a number theorist would call a pair of log general type. And in that setting, you don't need the modification of the base. Okay, so let me just now, state some sort of preliminary. So this has appeared on the archive. The uniformity results have not yet appeared, but let me just sort of give you an idea of the sorts of things that we could prove. Okay, so first, Langvoita says a pair xd of log general type on a pair of log general type. The integral points are not Zariski-Jones. Okay. And now sort of a remark is that Abramovich showed. So Abramovich did the same thing for the case of genus 1 curves, so elliptic curves minus the origin. Okay, so he did it for that, just for those pairs of log general type. He did it for elliptic curves minus the origin, and he showed that you need to restrict to what he called stably integral points. So instead of just taking an integral point, you have to look at instead stably integral points, which are points that remain integral after you do stable reduction. Okay.
What does it mean being Zariski dense for a pair?
Okay, I should probably say potentially dense or something. Right. So I think it's usually said are not potentially dense. Right, so okay, so maybe I should even say what an integral point is then. So, okay, so I have, so a model of a pair x comma d is, okay, so it's a family xd so that the general fiber x is equal to x. Okay, I don't need this k there. Okay, and the same thing for d. Okay, so this is what a model is now: an integral point. So let k be a number field. And let S be a finite set of places. Then an integral point is a section P from spec OKS to X. So that the support, the pullback B is contained in S. Okay, Okay, so how you should be thinking about this is to have a pair x, d. What I'm really interested is in the complement d inside x. I'm really interested in the quasi-projective variety x minus d. Okay, and so everything is respect to x minus d. So when I say something like dense, I mean with respect to x away from d. Okay, and so, and just to finish uniformity, so we prove that the S stably integral points on a curve of log general type are uniformly bounded. Okay. Okay, now in higher dimensions, I said things get sort of a bit more tricky, so we have to define a new notion of stably integral points because we don't have stable reduction in higher dimensions. So we define something called moduli stably integral, which has to do with the, we choose a canonical model for the moduli space of stable pairs, and then we use something that Abramovich showed in his paper to extend our notion. So this notion of moduli stably integral points restricts to the same notion of stably integral points for curves. So moduli stably integral points on a pair of log general type live inside a subscheme of uniformly bounded degree. Okay, and now you use this theorem, an induction, and some mild sort of technical hypotheses to extend this result to higher dimensions. But I think I'll stop there.
Is it explicit, the bounding term?